Wiggle room. I don't think they're gonna need longer than this, unfortunately. You can feed it, yeah, feed it.
Okay, let's get started. It's my great pleasure to introduce Noah Golowich. He is currently a PhD student at MIT and has had, for a graduate student, an incredibly prolific career who already has like really amazing results in a variety of areas, including online learning, game theory, classical pack learning. And today he's going to talk to us about reinforcement learning, which he has several great results in. So happy to have you here and excited for your talk.
Yeah, thanks for the introduction and thanks for inviting me to come and speak. So today I'm going to talk about computationally efficient reinforcement learning with linear Bellman completeness, and this is based on joint work with Ankur Moitra. Okay, so I'll begin by discussing some of the background on MDPs and reinforcement learning. I'll then talk about the particular model we work in, which is known as linear Bellman completeness. Then I'll discuss our algorithms and how our results are proved. So reinforcement learning in general describes the problem of learning in a dynamic or stateful environment. And it has numerous applications, such as learning in large-scale games, such as Go, robotics, healthcare, and recently it's been used to fine-tune large language models with great promise. The basic question that we're concerned about in reinforcement learning is, when is it possible to learn good policies in these dynamic environments? And I've worked on this question from numerous perspectives. One can take a statistical perspective and ask, what is the characterization of the optimal sample complexity of reinforcement learning? So we have some papers that address this question. But this talk is on the computational perspective. What are the challenges that we have to overcome for computationally efficient algorithms for reinforcement learning? And in this talk, I'm going to discuss some of these challenges for the problem of linear reinforcement learning. It turns out that there's numerous orthogonal challenges that also come up, like dealing with partial observability, representation learning, as well as multi-agent scenario. Okay, so reinforcement learning is typically modeled via the setting of MDPs, or Markov decision processes. And we'll consider finite horizon MDPs. These consist of the following components. There's a horizon capital H, an action set A, and a state set S. There's an initial distribution D over states at the first step. A transition kernel P of S prime given SA, which says if we're in some state and take action A, what is the probability of transitioning to some other state, S prime? And finally, there's a reward function R of SA, which gives the reward the agent receives if they're in some state S and take action A. So how do these pieces fit together? Well, a trajectory in an MDP consists of a total of capital H steps. Initially, some state S1 is drawn from the distribution D. And at each step, little h from 1 to capital H, the agent observes its current state SH. It chooses an action AH according to some policy. And then it receives some reward R of SH and AH, and it transitions to a new state SH plus 1 according to the transition kernel P. So this process repeats for a total of capital H steps. And the decisions the agent takes along this trajectory, namely its actions, are chosen according to a policy, which formally speaking is just a tuple of mappings, pi1 through pi capital H, where each pi little h is a mapping from the state space to distributions of our actions. It tells us what action to take as a function of the state. I'll let capital pi denote the set of all policies. And associated to any policy are two important value functions known as the Q value function and the V value function. The Q value function of policy pi, Q pi of SA, some step h, is defined as follows. It's the expected cumulative reward if we start at state action pair SA at step h, and thereafter follow the policy pi to choose subsequent actions. And we're summing the rewards from step little h to capital H. The V value function VH pi of S is simply the Q value function at state S, where we're taking an action according to pi of S. So the value of a policy is just the expected value, the V value function at step 1 for an initial state drawn from the distribution D. Alternatively, the value is just the sum of rewards and expectation where we're following the policy pi. And our goal in reinforcement learning is to learn a near optimal policy, where an optimal policy is simply a value maximizing policy. So I'll call pi star the optimal policy. Now, how do we find the some policy pi hat, which has near optimum value? Typically, we're going to proceed as follows. We have some number t, denoting the number of episodes. And in each episode, little t from 1 to capital T, the agent chooses a policy, I'll call it pi t. It executes it, observing a trajectory consisting of states, actions, and rewards from the policy. And then it uses its data to choose another policy, pi t plus 1, and repeats for a total of capital T episodes. After these episodes, it's going to output the policy pi hat, which should be near optimal. So you should think of the parameter t as denoting the sample complexity. We're going to measure the number of samples, or it's just the number of episodes.
Wait, so does the agent always know what state they're in?
Yes, they always
Okay,
observe.
So it's not partially observable. It's
Not partially.
and there's no exponential discounting. So
There's no
just-
exponential.
Okay, so it just we run for some known finite number of steps.
Exactly.
Thanks.
Yes. Okay, so that's the general setting. Now, a major challenge in reinforcement learning is that the state space is often enormous. So for instance, in the game of Go, the state space would be all possible configurations of the game board. This is exponential in the size of the game. And as such, it's not even clear how we can represent all of these. These have to map these enormous state spaces to the action space. So to address this challenge, it's typically people use an approach known as function approximation in reinforcement learning. And here's what function approximation typically does. We're first going to compute some sort of value function. I'll call it Q hat, mapping from the state action space to real numbers. And you should think of this as some estimate of the optimal value function Q pi star. So pictorially, we have the state and action. There's maybe some neural network which computes Q hat. And given Q hat, we can consider the greedy policy. I'll call this pi hat of S, which at each state S just chooses a value maximizing action according to Q hat. So argmax over A of Q hat of SA. Now, if Q hat is a good estimate of Q pi star, the greedy policy will be near optimal. And the hope here is that Q pi star is indeed well approximated by some class of functions that we can learn, such as neural networks. But even if this hope is satisfied, it's not clear how we can actually find such a good approximation to Q pi star. After all, we're not giving labeled pairs of state action pairs together with Q pi star of that state action pair. We somehow have to explore the environment and find enough good state action pairs to use as data. So to address this problem, a typical approach proceeds by first making the following observation, which is that Q pi star satisfies what's known as the Bellman equation. In other words, Q pi star, some state action pair SA, is equal to the immediate reward plus the expected value of Q pi star at the next state S prime drawn from the transition kernel starting at SA. The fact that this holds is just, a simple argument via dynamic programming. I'm just restating the fact that dynamic programming can be used to compute the optimal value function of MDPs.
What's R again?
R is the reward function, so it's the reward I receive in a single step. Now, the quantity shown in red, this expectation, is quite important, so we have a special name for it. We're going to call it the Bellman backup, the Q value function at step h plus 1. And I'll denote it as T Q h plus 1 pi star. The operator T, which takes as input this function, this value function at step h plus 1, and outputs some function at step h, defined by this expectation, is called the Bellman operator. And basically what the approach that's suggested by this Bellman equation is known as value iteration. So what value iteration does is it repeatedly approximates this dynamic programming approach. So in the first step, we're going to find some estimate Q hat capital H of the value function of step capital H, which is just the reward of that step. Then given this value function Q hat capital H, I'm going to estimate the reward function plus its Bellman backup. I'll call that Q hat H minus one, and I'll repeat this procedure for a total of capital H steps. So each step having computed some estimate Q hat H plus one, I'm going to compute some estimate Q hat H by approximating the reward function plus the Bellman backup of Q hat H plus one. So that's the overall idea. And one thing I haven't told you is how we actually estimate these Bellman backups in value iteration. So I've formally written out the definition of the Bellman backup on the top. It's just taking this function QH plus one and computing this expectation. Typically, to actually estimate these value functions, we have to solve some regression. So a very standard approach is to use least squares regression. So for a function class f of bounded complexity, often what we do to estimate these Bellman backups is to solve this least squares problem. We assume that we're given some data set D consisting of tuples of state, action, reward, and subsequent state. And we're going to choose a function QH in this class f so as to minimize the mean distance between QH of SA and this target label shown. This label is just reward plus the quantity you can think of as the empirical estimate of what's in the Bellman backup. And as such, we would hope that the result of this regression problem is a good approximation to the reward plus the Bellman backup of Q hat H plus one. And this will indeed hold if two conditions are satisfied. The first is that the data set D is sufficiently exploratory, so we're given enough diverse data. I'll say more about what this means later. But second, we need this regression problem to be well specified. In other words, the expectation of this target label must actually belong to the class F that we're choosing, that we're optimizing over. And what does it mean to be well specified here? Well, this expectation is basically just the Bellman backup. So what we need is that for all possible value functions Q hat H plus one, its Bellman backup belongs to the class F. Yeah. Sorry.
What is H?
What is what?
Hat.
Hat. Oh,
H.
H. Oh, H. H is just a timestamp. So it,
Assume you know Q hat H plus one and your instead of this.
yes, we know Q hat H plus one. We're trying to find Q hat H. Yeah, so Bellman completeness says the following: for all value functions Q hat H plus one at the next time step, which lie in our value function class, we need the Bellman backup to also lie in the class F. So it's a sort of natural closure property for our value function class. We take something in the class, we take the Bellman backup, we should get something that's also lies in the class.
So, like the way I understood that AlphaGo works is like that you iteratively, like you learn a neural net to evaluate a position. And then you do like Monte Carlo tree search with that neural net at the leaves. And then you learn a new neural net that approximates that. And keep repeating, like is Bellman backup like another way of saying that?
I think so. I guess
Okay.
we'd have to get into more
All right,
details.
but what you're describing, it is how AlphaGo works?
This is
Yeah.
not exactly how AlphaGo works.
Not
I
exactly.
don't know exactly how AlphaGo
All right,
works.
because you did use that example, but all right. Okay.
Yeah, I mean, like, basically, when you move from the theory to the practice, there's many
Yeah,
additional
fine,
subtleties that
fine,
come up, so.
Fine.
And actually, is there one question? Yeah.
So the Bellman completeness, is there an assumption? Are you assuming that or does that?
Yes, it's gonna be an assumption. You have to make the assumption on the MDP. So in general, MDPs will not like necessarily satisfy this.
So Q hat, that's defined like on this real data set of particular samples, right? Compared to Q, which is just, an expectation, right? So the Bellman completeness condition, is that basically dependent on the samples because?
It's not dependent on the samples. Q hat is, we're basically saying that for any Q hat at step H plus one, this should say in F. For any Q hat H plus one in F, Bellman backup is also in F. So Q hat is just an arbitrary function in the value function.
Right, but the way that you're defining the backup operator empirically, like in the second equation here, you're defining Q hat in terms of the, Q hat H in terms of Q hat H plus one in terms of sample, like that definition depends on samples.
This definition depends on samples, but the definition of Bellman completeness does not depend on samples.
But the definition of the operator does.
No, it doesn't. Like the operator T is defined at the top. So it's just an
Oh, okay.
expectation.
So that should really just be on Q then, when you're saying Bellman, not Q hat.
Yeah, I mean, you can replace this, like, this is just the page.
It's a variable, I
Yeah.
see, okay, fine, but you see what I'm saying?
Yeah, I mean, sure. Okay, and actually, sorry, is there another question? No, okay. So basically, the specific setting that we're going to be focusing on is when the value function class F consists of linear function. And this is actually a setting in which we can hope to get computationally efficient algorithms in a provable sense. And when you make this linearity assumption, you actually get the assumption of linear Bellman completeness. That's what Bellman completeness is called in the linear setting. Yep.
So if a function class is complete, does that mean it contains the Q, the true Q function?
Yes,
Or
it
contains
does.
something close to it?
It contains
You can prove
the Q value function. You can prove this, yes. That's basically because the Q value function, the optimum one, is defined by iterating Bellman backups. So you do get that property.
Is the optimal policy the fixed point of the Bellman number?
In the discounted setting, yes. Because we're looking at the non-discounted setting, fixed point doesn't really make sense, but in the discounted setting, yeah. Okay, so that kind of motivates the definition of linear Bellman completeness. Now I'm just going to formally define what it means in a more streamlined manner. So given a feature mapping phi from state action pairs to d-dimensional vectors, I'm going to let script B denote the set of all vectors in RD, which have bounded inner product with each feature vector. So you should think of B as indexing the set of bounded linear value functions. And we say that an MDP M satisfies linear Bellman completeness with respect to the features phi if there's a mapping T, the Bellman operator, from the set B to itself, together with the reward vector W, which satisfy the following two conditions. The first condition says that linear value functions should have Bellman backup, which is linear. Linear value function reduced by theta. Its Bellman backup is a linear function whose coefficient vector is phi of theta. And the second condition is simply saying that the reward at any state action pair is a linear function of phi of SA, the coefficient being W. Okay, now why should we care about linear Bellman completeness? One of the things I like about linear Bellman completeness is that it unifies most of the settings in RL and control theory where we have computationally efficient algorithms that are known. The simplest setting of this is maybe tabular MDPs, where we assume that the state and action spaces are small, and we aim to get algorithms whose running time and sample complexity is polynomial in the number of states and actions. Of course, that's not a particularly realistic assumption. So people have tried to generalize this. And one of the generalizations of tabular MDPs that's quite popular is that of linear MDPs. A linear MDP is one whose transition matrices are linear in the features phi of SA. Unfortunately, this implies that the transitions are low rank. Their rank is at most the dimension D of the features. And this low rankiness precludes linear MDPs from capturing certain natural physical models of dynamics, like linear dynamical systems. We also have computationally efficient algorithms for certain models of linear dynamical systems with control. And linear Bellman completeness is nice because it unifies all.
So again, in linear Bellman completeness, the thing that is linear is the model that you're using to like approximate the optimal policy, or what? What's the linear part?
The linear part is the fact refers to the fact the value function class is going to be linear. So like this class F. F consists of functions that are linear.
Okay, fine.
The model may not be linear.
Fine, all right, got it. And it's linear in what?
Some known feature mapping.
Oh, all right, fine.
So one of the advantages of focusing on these more general models like linear Bellman completeness is that it may lead us to more general purpose algorithms that work not only in all of these settings, but also potentially other settings where we haven't yet written down and may capture what we want.
So this definition seems very broad. Is this an easy condition to satisfy?
That's a good question. So it's, here's some examples of the things that satisfy it. You can come up with other kind of,
But you have to assume some like new dynamics.
there obviously is going to be some notion of linearity, and that is a limitation. But if you want computationally efficient algorithms, typically we can't solve, even very simple nonlinear regression problems efficiently. But you do have to restrict yourself quite a bit if you want a computationally
That
efficient.
this tropical algebra where you replace the sum with max and the product with plus. Then like these max linear forms are actually naturally, I think will be more natural for this kind of companies.
Okay, I be interested in hearing that.
This T by theta, is that T evaluated at theta or T times theta?
It's T is an operator, so it's T of theta. T maps the set bounded of vectors to set of vectors. Okay, so what is known about learning with linear Bellman completeness? One of the basic results here is that it's known that an epsilon optimal policy can be learned with a number of samples that's polynomial in the dimension, the horizon, and 1 over epsilon. Unfortunately, even though there's a number of algorithms, maybe 4 or 5 different ones that are well known that achieve this sort of guarantee, all of them are computationally inefficient. And that's because they have to solve a certain non-convex optimization problem. There has been work on getting computationally efficient algorithms for learning with linear Bellman completeness, but these works all make additional assumptions. So one common assumption is known as reachability, which roughly speaking says the following: for any feature vector direction in RD, there exists some policy which visits features at an expectation point in the same direction. The problem is that reachability is a pretty strong condition. For instance, there may be certain directions which we just can't reach with any meaningful policy. For instance, at least currently known humanoid robots can't fly. So if there's some feature direction which represents robot flying, you can't reach that. And as a result of the fact that these algorithms are only fairly specific, the general question of whether there's a computationally efficient algorithm for MDPs satisfying linear Bellman completeness has remained open. Now, before discussing our main result, which makes progress towards this question, I want to say a few words about why we should care about computational efficiency in this setting. Roughly speaking, the question of coming up with computationally efficient algorithms answers the question of whether having a good representation or feature map of our state action space is enough for efficient reinforcement learning. I like to think about this in an analogy to linear regression. We know that for regression problems, if we have a good feature map, in the sense that the targets are linear in this feature map, that is enough for efficient learning because linear regression can be performed computationally efficiently. But RL is more analogous to some alternate universe where linear regression were not computationally efficient. And because we don't even have good algorithms for linear reinforcement learning, you might expect that we don't really have the right abstractions or techniques that can make reinforcement learning more efficient in nonlinear, more complex settings as well. And in fact, there has been quite a bit of work which is aimed to understand reinforcement learning better in the setting of linear function approximation. So one of the weakest assumptions you can make on RL with linear function approximation is that the optimal Q-value function is linear in the feature. And there was a question about this earlier. This is indeed implied by Bellman completeness. And it is, in fact, enough to enable statistically efficient algorithms. The number of actions is a constant. But it's known that unless NP equals RP, there's no computationally efficient algorithm for this problem. So you want computational efficiency, just linearity of Q star is not enough.
Question. So in other words, this is, I think this is a weaker assumption than linear Bellman completeness.
Yes.
That implies it.
Exactly, yes. Now, a much stronger assumption on the other end of the spectrum is linear MDPs. These are where the transitions are linear in phi of SA. And as I mentioned, we do have computationally efficient algorithms for these, but they're not, it's too strong of an assumption. It doesn't allow us to model things like linear dynamical systems. So linear Bellman completeness lies in the middle here, a kind of sort of happy middle where we know that there are statistically efficient algorithms, It does model things like linear dynamical systems, but it was open as to whether or not you can get computationally efficient algorithms. So our main result makes the first progress towards this question of getting computationally efficient algorithms in general. What we show is that there's an algorithm that learns an epsilon optimal policy of an unknown linear Bellman complete MDP using a number of samples, which is polynomial all parameters and exponential in the number of actions, using the same amount of time. So for most of the rest of the talk, I'm going to discuss how we prove this theorem. The main challenge in the proof is to solve the exploration problem. In other words, how do we adaptively explore new states? Now, why do we care about this? Well, if you recall a few slides ago, I mentioned that the sort of meta algorithm that people use is least squares value iteration.
Oh, no, just looking ahead, just a brief question, like, if you're exponential in the number of actions, then it sounds like you are exploring you are like exploring the entire space. Like there's no exploration, because that is the size of the entire space of all possible actions you can take. Or
Well, no, like
that's not
the number of like the number of policies is like a to the s. So s is in the exponent.
oh I see.
And then even there's a lot of interesting MDPs where exploration is non-trivial with even 2 actions. So like the key point is that you can kind of branch out a lot in the state space. So we're doing exploration in the state space in a non-trivial way.
So yeah, so where is the dependence on that?
There is no dependence on that. That's being handled by the linearity. The D shows up in the right here.
I see.
D is the dimension of
The feature mapping. Yes, exactly. So if we can perform exploration and get this data set D, then we just use that in the context of least squares value iteration. And so really exploration is the key challenge. Yeah.
So in generating these samples, you don't care about what reward you're getting. This is just pure explorer, right? Your algorithm is, I guess that's my question. Like, is your algorithm just like, this is the way to pure explore, forget about the reward while you're exploring. And at the end of that, with this many samples, you'll get the optimum policy.
Yeah, exactly.
Okay.
Now, yeah, you can, yes, that basically our algorithm is doing this kind of pure exploration. We also have, it turns out that the policies we use for exploration will also be good policies in the end, but this distinction between exploration and exploitation isn't really an important factor for us. So to explain how we do exploration, it's useful to consider a simpler bandit setting, which is the special case where there's a single state and there's multiple actions. Each action gives some stochastic reward, and our goal is to find the action or choose an action with near optimal expected reward. So the expected rewards are just the value functions in the setting, and those are shown in green in this little picture. Now suppose that in the bandit setting, we're in the middle of some algorithm, and we've computed some estimates, I'll call them Q hat, shown in red, of the expected reward for each action. Suppose that it just so happens that A star, the optimal action, has not yet been explored by much. And a result of random error, our estimate Q hat of the value of A star is a lot less than the true value Q star of A star. If this is the case, then the greedy policy, which simply chooses an optimal action according to Q hat, will fail to explore the optimal action A star. This is because maybe we'll choose the 8th action, the first action, when we find these estimates a little bit, but this red bar is much, much lower than what we're going to refine them to, so we'll never get around to choosing A star. Typically, the solution to this is to add exploration bonuses. So for each action, we're going to add a bonus, which is inversely proportional to how much we've explored that action in the past. Because A star has not been explored, its bonus is going to be much larger, and so we'll choose it, explore it more, and ultimately bring up our estimate of the value of A star. So how do we choose exploration bonuses? In principle, roughly speaking, there's 2 requirements. First of all, we need the bonus to be large enough so as to induce us to choose the right action. And in general, typically we want our estimates Q hat plus the bonus to be an upper bound on the optimal value Q star. Now, of course, the trivial way to satisfy this condition is just to choose every bonus to be infinity. The bonuses have to ultimately tell us some information. They have to decrease at a certain action as we explore that action more and more. And this will ultimately let us hone in on the right action to take. So these two factors are a little bit at odds with each other. One says the bonuses can't be too small. The other says they can't be too large. And we move to the more complicated RL setting. There's actually a third property that our exploration bonuses must satisfy. And this has to do with the fact that we're using regression, linear regression, to solve the value iteration problem. You recall that the whole reason I wanted Bellman completeness or linear Bellman completeness was to make sure that the regression problem is well specified. But if I'm now adding bonuses to my value functions, it better be the case that my bonuses don't break this Bellman completeness property. And so basically what I want is that the Bellman backup of the bonuses that I add should be a linear function. And so this third requirement actually turned out to pose a lot of problems in performing exploration with linear Bellman completeness. Our paper is the first that really deals with balancing all three of these issues simultaneously by means of a computationally efficient algorithm. So before telling you exactly what we do, I'm going to discuss a few natural approaches to try to solve these three issues simultaneously. And some of these approaches appear in prior. So one approach is known as global optimism. What global optimism does is it chooses policies by solving a certain non-convex optimization problem, which asks, how can we find the ideal exploration bonus which simultaneously satisfies these three requirements? This is exactly what gives statistically efficient algorithms. So it works, but as I mentioned, it's not computationally efficient. The other approach which is out there is known as local optimism. And this is more akin to a generalization of the approach I mentioned in the previous slide, which adds exploration bonuses for the bandit problem. And so in particular, local optimism adds an exploration bonus to each state of size, which is determined in some sense by how well explored each state is. Typically, this will meet the first two requirements. And as such, it will work for certain more restrictive models like linear MDPs. But it fails to satisfy this third requirement, which is that bonuses have to satisfy this Bellman completeness property. So what we do is we actually take this local optimism. We're going to find a way to make local optimism work in the context of linear Bellman complete MDPs. Okay, so now I'm going to describe our algorithm. It'll describe how the bonuses fit together with the value iteration. And after giving you an overview of our algorithm, I'll then describe what particular bonus we use. So the algorithm is called PSDP-UCB, or Policy Search by Dynamic Programming with Upper Confidence Bounds. And it's a variant of the approach that was used for solving linear MDPs. In each episode T, we're going to do the following. We're going to go backwards in terms of the steps. So go from the final step, capital H, all the way down to the first step. And here's what we'll do. We're going to draw a bunch of samples, say n samples, from a uniform mixture of policies that we've explored in previous episodes. So I'll call these policies pi hat 1 through pi hat t. I'll then let sigma ht be the covariance matrix corresponding to the feature vectors at step h of these samples. Sigma t, roughly speaking, captures which directions we've explored. It's going to be larger in directions where we have more feature vectors pointing in that direction and smaller in other directions. So sigma ht is then going to be used to construct this bonus function, mapping from states to non-negative reals, which gives a bonus, an exploration bonus for each state. We can then use this bonus function to define optimistic rewards, RGI hat, for all steps g bigger than the current step h. These are going to be the true rewards RGI, plus the bonus function evaluated at the state SGI for each sample I in our data set. These optimistic rewards are then fed into a least squares regression problem. So we're going to consider the least squares problem where you have feature vectors phi for each sample I in the data set. And the labels are just going to be the sum of optimistic rewards for steps little h to capital H. The solution to this least squares problem, which I'll call W hat H, is then used to define a policy just by considering the greedy element. That's called pi hat HT of S. And this policy pi hat HT is then going to be sampled from in subsequent episodes. And the idea here is that the bonuses should induce W hat and thereby the policy pi to point in directions which will ultimately lead to unexplored states. And so after a total of capital T episodes, we're just going to output one of these policies pi hat 1 through pi hat t at random. And we're going to claim an expectation that this the expected value of this thing will be close to the near optimal.
So where and how does this differ from the things people do for linear MDPs?
Good question. So there's a few ways. Maybe the most significant is the bonus is different. But also for linear MDPs, the targets in the regression problem were not actually the rewards from some policy, but it was actually directly the estimate of the value function we computed the next step. And so that's why for linear MDPs, it's called LSVI, where the regression targets are the value function. It turns out that for technical reasons, we actually need the regression targets to be these stochastic rewards. But morally, they're kind of similar.
Okay, so isn't your bonus just like taking the inverse of sigma t and taking it between the five?
That's not going to be our bonus.
That's not your bonus.
That's not our bonus.
Okay, so maybe that's it.
Yeah, that's the main difference. Yeah. So that's the we'll talk about that. Yeah.
If you could evaluate which of the previous policies is the best one and use that one, would it work, or you need to take the mixture of the past policies?
You need to take a mixture because you need some sort of diversity. You need some sort of exploration. Yep.
This gives you guaranteed expectation.
Yeah, so the expected value, the mean of the values of pi hat 1 to pi hat t will be your
Maybe I missed something, but why is the bonus function only a function of the state and not also the action?
It could be a function of the action. It just turns out to be simpler for us to make it a function of just the state.
Because in your single state example that you gave for intuition, it needed to be a function of the action.
Yes.
So somehow it's okay to drop that.
Yeah, so one trivial way to explore if there's this finite number of actions is try every action a bunch of times. And since we have a small number of actions, exploring an action space is. Yeah, so it's like really the hard part is exploring the state space, not the action space for us. Okay, so I now have to kind of fill in this missing piece, which is how do we construct the bonuses? And the natural choice, kind of what one of the last questions alluded to, is that maybe we should just try what they used for LSVI, which works in linear MDPs. And so this looks like the following quantity for each state. We're going to look at a maximum number of actions of the norm, the feature vector phi of SA, measured with respect to the inverse covariance matrix of features that we've seen so far. This fails in the following sense. It does not satisfy this third Bellman completeness condition that we want our exploration bonuses to satisfy. The Bellman backup of this quadratic confidence bonus FH quad is not a linear function. So you might think, okay, we can maybe modify this in some. One bonus which actually has similar properties to the quadratic confidence bonus is what I'll call the randomized bonus, FH normal of S, which first draws a vector W from the normal distribution with mean 0 and covariance given by sigma inverse. And it looks at the expectation of this linear function. This randomized bonus does satisfy the desired linearity property. The Bellman backup is a linear function. And moreover, it's an approximation to the quadratic confidence bonus in a certain sense. And you might think that this will make it satisfy the first two requirements. It turns out that there's a subtle issue here that really kind of leads to a lot of technical challenges. It's that using the normal confidence bonus leads to exponential compounding of bonuses. And basically this occurs for the following reason. We need to choose the bonus at some step h to be large enough so as to cancel out errors that we've made in estimating the value function plus the bonus at the subsequent step. As a result of the guarantees we can get from linear regression, the errors are going to be like a poly d factor times the size of the bonus at step h plus 1. And so we need the bonus at step h to be at least a poly d factor times the size of the bonus at step h plus 1. And this is going to compound over a total of h steps. It's going to give us exponential h dependence, and that's undesirable. So our main the core of our technical contribution is a way to solve this issue. And we do this by introducing what we call the truncated linear bonus. Given orthogonal vectors u and v in d-dimensional Euclidean space, we define the truncated linear bonus at a state S for vectors u and v to be the sum of the following three terms. It's going to be the max over A, the inner product of u and phi of SA, the same thing for v, and we're subtracting off the same thing for u plus phi. The actual bonuses FHT that we use is simply the expectation of the truncated linear bonus over vectors u and v drawn from appropriate Gaussians, whose covariance matrices, roughly speaking, represent the explored and unexplored directions.
Why is it called truncated?
Good question. I'll get to that in one moment. So how does this avoid exponential blow? Well, let me explain how exponential blow is avoided in the case of linear MDPs, because a similar compounding error might occur there. Typically, what's done in linear MDPs is you take the minimum of the quadratic confidence bonus and the horizon capital H. And so you're truncating the bonuses. Now, this works in linear MDPs, but taking a minimum of a constant H and say the randomized bonus from the previous slide will actually once again break the Bellman linearity. Will break the fact that the Bellman backups are linear. And the idea is that the truncated linear bonus essentially simulates this truncation, this minimum, in a certain sense. And roughly speaking, you should think of this truncated linear bonus as kind of acting similarly to the min of the first two terms here, if u and v lie in a certain good region of Euclidean space. And what our algorithm or what our analysis shows is that the vectors u and v, when drawn from these Gaussian distributions, will lie in this good region of Euclidean space with probability roughly 1 over exponential in the number of actions. And this is ultimately what leads to the exp-A dependence in our computational stable call. We have to add some exp-A factor outside our bonus function to make it large enough so as to compensate for the fact that it's only acting in the desired way with exp minus A probability. How much time do I have?
Is any chance you can finish in 5 minutes?
Yeah, easily. Yeah. Was there a question?
Yeah. That's a good question. So U and V here are going to be generated from sigma inverse, the dot chain with sigma inverse.
Yes. So U and V are going to be they're going to be defined from sigma inverse. Basically, we kind of split it up into two parts. Yeah. Okay. So let me just finally explain how all the individual pieces fit together. The way the proof proceeds is we're going to define some optimistic value functions associated with pi hat t. There's an optimistic Q value function QH bar, which is simply the expected sum of rewards from step H, the final step capital H, plus the expected bonuses FGT. And we'll define an optimistic value function V bar, which is simply the optimistic Q value function in a state S, and where the action is according to pi hat t. And we show two lemmas. First of all, with high probability, this optimistic value function is indeed an overestimate, an upper bound in the true value function. The second lemma is an upper bound on the size of the individual bonuses. We're showing that the individual bonuses are bounded by the quadratic confidence bonus times some exponential in A. Yeah, kind of the main lemma is lemma 1. This is where kind of the main properties of the bonus are being used. Once you have the two lemmas, the proof is actually fairly immediate. Basically, what we can do is we want to bound the average suboptimality of the policies pi t, their algorithm outputs. We can first apply optimism, which upper bounds v pi star with our upper optimistic bonuses v bar t. Then we can just use the definition of the optimistic value function together with the true value function and cancel out the expected rewards in these definitions. This gives us the expected value of the bonuses. And finally, we can use the second lemma together with a standard result known as the elliptic potential lemma, upper bound the sum over all time steps of the expected confidence bonuses with something that decays as t goes to infinity. So if t is large enough, we get that we're near optimal. Okay, so we also have some analogous guarantees in what's known as the offline setting of reinforcement learning. There we're able to get a computationally efficient algorithm that scales polynomially in all parameters, not just in particular number of actions as well. So I'm happy to talk about that offline. Finally, I'll just mention, some other work that I've been interested in. I'll be around the rest of the day, so I'm happy to talk about any of these things. We're working in online learning and game theory, so we have some optimal convergence rates for knowing about learning in games, as well as some work on no swap regret. So we have the first polynomial time algorithm to approximate correlated equilibrium in extensive form games. And I've also been interested in the sequential calibration problems. We have some improvement on the classical bound of Foster and Verwa. And additionally, I'm interested in privacy. So I've been working on private pack learning, as well as in recently I've been interested in watermarking as well. So just to summarize, we gave the first computationally efficient algorithm for online reinforcement learning with linear Bellman completeness, when the number of actions is a constant. We also have an analogous guarantee for offline reinforcement learning. There's many open questions. Maybe the most obvious one is extending our algorithm to work for larger values of actions. So